Let's take that last thing a step further and talk about something called linear independence. So this left-hand side right here is a linear combination, and I change from C's to K's. Let's go all C's there. So let's consider the equation C1V1 plus 2CnVn equals 0. So a linear combination of vectors equals 0. So if all the CI's are 0, it's clearly true, right? So you get 0 plus 0 plus 0 plus 0 plus 0. That's called the trivial solution. If the trivial solution is the only solution, then the set of vectors are called linearly independent. Linearly independent. If not, then the set of vectors is called linearly dependent. Okay, so for our first example, let's show that the vectors 1, 1 and negative 1, 1 are linearly independent. Okay, so what do we need to do? So A times the first plus B times the second equals 0. Now, again, this is obviously true when A is 0 and B is 0. And what I need to show is that that's the only one. How do we do this? Well, again, look at this. It says A plus negative B, right? A plus negative B equals 0. And then A plus B equals 0. So this effectively makes a system, right? And I'm not going to bother going to a matrix for this one, just add them up and I get 2A is 0, and so that means that A is 0, and if A is 0, then what does that mean? So 0, let's do the other one, 0 plus what equals 0, and the answer is 0. So that means that B equals 0 also. So I mute my computer. Okay, so we just showed that A is 0 and B is 0. Okay, now remember what we did in our last video. We took this equation right here, and we effectively said this looks like A, 1, 1 plus B, negative 1, 1 equals 0, 0, right? And just realized I used a bit of, sloppy notation here. This is the 0 vector, right? The 0 vector, not the 0 number. That's where that came from, okay? All right. So this really amounts to, if I have 1, 1, negative 1, 1, 0, 0, if this thing row reduces to the identity, right, then it gives me the trivial solution, which means it's the only solution, right? Okay. Let's try another. So what about 3 vectors? That, and that. Are they linearly independent? Okay, well, I have 3 this time. So A, 1, 1. B, 1, negative 1. And C with 2, 0. And let's make the 0 out of this one. Maybe you're sort of feeling what's going to happen already, because what I have is 1, 1, 2, 0. 1, negative 1, 0, 0. Now, this is going to row reduce something like this, okay? I don't really know. I don't really care about doing it. I'm going to be able to get 2 leading ones here, I think. Those are very similar to the ones that we just did, but these 2 things are not going to be zeros. And even if they are zeros, I don't care what they are. The whole point here is that this is going to be a free variable. And so there's not going to be just one solution here. There's going to be infinitely many solutions to this thing. And so I have 3 vectors that effectively can't be linearly independent, okay? So these are definitely dependent, okay? Now, you might actually need to come up with what is the linear combination of these things that makes 0, and we can probably tell just by looking at it. So why don't we just try that real quick? Let me move this over here. Can I actually just think of the linear combination that makes these 0? I lost a bracket there. I think that 1, 1, if I add that to 1, negative 1, that's going to give me 0 there and 2 there. If I take away 2, 0, that gives me 0, 0. So that means that one of those plus one of those minus one of those gives me the 0 vector. Okay, so that is the linear combination that I need. And if you need to come up with one, then there's really just kind of some fiddling around here. And on this one, there are infinitely many possibilities. So all you have to do is find something that satisfies this thing right here. All right, the next one. linear independence in R3. So determine whether or not the following set of vectors is linearly independent. So I have 1, 2, 3 vectors here. Again, I'm going to kind of skip the middle step here. All I really have to do is make them the columns as you saw in the previous example. So I've kind of shortened this process up here. If what I get is the identity, then it's going to be the trivial solution. If I don't get the identity, then something else. So let's just try that. So I need to go to my matrix land. My second button's not working. There we go. Let's edit matrix A, 3 by 3. And it's 3, 0, 2, 0, 1, 3, 1, 2, 0. Okay, now you might say, well, that's a 3 by 4. And you're right, it's a 3 by 4, but I don't really care about these. It's going to be 0 over there anyway, so I can save myself the step there. And let's just enter this to make sure I've entered it right. 3, 0, 2, 0, 1, 3, 1, 2, 0. Good. And let's row reduce that. And I do indeed get the identity. So this row reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1. Which means that these are linearly independent. Now here's something that I actually find to be the most useful kind of way to think about linear independence. So here we go. A set with 2 or more vectors is linearly dependent if and only if at least one of the vectors in S is expressible as a linear combination of the others in S, okay? So again, what does that mean? If I have some C1, let's just go 3 vectors here. Suppose I have 3 vectors, v1 and v2 and v3. And then I have some c1, c2 plus, oops, I left myself the wrong space, plus c3. Suppose that equals 0. Well, if I can write a linear combination of these, then I could just take one of them and move it over, and then say that c1 v1 plus c2 v2 is equal to minus c3 v3, right? And that's what this is saying. Then some one of them is a linear combination of the others, right? You could divide by the c3 if you want to. So that's what this thing is saying here. So they're dependent if and only if one of them is a linear combination of the others. Okay, and then number 2 is basically saying the opposite. They're independent if and only if no vector is expressible as a linear combination of the others. All right. Now, kind of as a corollary to that, if there's only 2 vectors, then they're linearly dependent if and only if one of them is a multiple of the others. All right. So here we go. Are the rows of the following matrices dependent or independent? And we're just going to do it by inspection. Okay, let's see. So I have the row here 2, 3, and the row 4, 6. 2 times 2 is 4, and then 3 times 2 is 6. Okay, well, there we go. So this row is a multiple of the first row, so these rows are dependent. Okay, let's try the second one. I have 2 rows here, 1, 5, 7, 3, 1, 5. 1 times 3 is 3. 5 times 3 is 15. Okay, what's 7 times 3? 21? Nope, that's not 21. And so these things are independent. Okay, now I have 3 rows. And the 3s are a little bit trickier to do, although I think I intended this one to work out right. So what do we know here? I want to use this, this theorem right here. So what do you get if you add the first row and the second row? So 1 plus 0 is 1. 2 plus 1 is 3. 0 plus 1 is 1. So what we have here is row 1 plus row 2 is equal to row 3. And so that means that the rows are dependent. Or I should say that the rows form a dependent set of vectors. Go back to my cooking example here because I think this is fun. So here's a fun fact if you ever made biscuits or something. If you mix 1 cup of all-purpose flour with a half teaspoon of salt and 1.5 teaspoons of baking powder, you have about a cup of self-rising flour. So if you make biscuits, you need self-rising flour. Or if you don't have self-rising flour, you can just make your own like I do. And so here's the question. Is the following set dependent or independent? Water, flour, salt, yeast, baking powder, and self-rising flour. And the answer is dependent. Why? Because I just told you that you can make self-rising flour out of baking powder, not yeast, but the wrong one, salt, and flour. So I don't need this in my kitchen. I can make that out of other things in my kitchen. Okay, again, this isn't really an example of a vector space and all that kind of stuff, but I think it does get the point across about what dependence means. If you can make one of them out of the other ones, then they are dependent. Okay, the next time we'll talk about span, and I'll see you then.